Hi everyone, welcome to the NOAA Central Library. We're very pleased to have Dr. Li here. Dr. Li has a Ph.D. in physical oceanography from the Northern Carolina State University. He's been supporting the National Environmental Satellite Data and Information Service, NESDIS, ever since. He's authored more than 130 peer-reviewed publications and edited 3 books, and he currently serves as an associate editor of IEEE Transactions on Geoscience and Remote Sensing, and as the Ocean Section Editor-in-Chief of Remote Sensing. So please join me in welcoming Dr. Li and his presentation on Spaceborne, synthetic aperture radar, and tropical cyclone monitoring. Okay, take it away.
Thank you very much. First of all, I would like to thank NOAA Central Library to give me this opportunity to present this seminar. And thank Katie and also Laurie from STAR for putting this talk together. And again, my name is Xiaofeng Li. I support NOAA NESDIS SAR activities. This work is not myself alone. We have contributors from NOAA NESDIS SAR team led by Sean, and I acknowledge my colleagues Frank Monado and Chris Jackson. Jun Zhang from AOML, Hurricane Research Division, also made a significant contribution to this research, along with a couple of students from Canada. Let's see if it doesn't. Okay, so this is the outline of my talk. First, going to introduce what this new instrument is, and then I will talk about the application of the synthetic aperture radar applications in hurricane monitoring, including morphology, winds, rain, waves, and so on. So remote sensing observation of oceans, there are primarily 2 types of instruments. One we call the passive remote sensing instrument. Another one is called active. Those instruments were first flown on board the CSAT mission in the 1978. And for passive remote sensing, basically you observe ocean sea surface temperature, ocean color, salinity, so on. For active remote sensing, we have an altimeter to measure the dynamic topography. You have the scalerometer to measure ocean surface wind. And then this comes our instrument, the synthetic aperture radar, which really observes the 2-dimensional sea surface roughness in a very, very high spatial resolution. So what is a synthetic aperture radar? We call it SAR. And what's the difference between a real SAR and a real aperture radar and the synthetic aperture radar? It comes into the ground resolution differences. For example, for the regular radar, the spatial resolution calculation is very, very different from the SAR in the cross-range along track direction. For the range direction, they are more or less the same. Let me just give you an example. For range in range direction, you can see this is range direction, is a along track, we call it azimuth direction. In the range direction, the real radar, if you put in orbit, is something like you can achieve like 3.7 meter to 15 meter resolution. That depends on the radar characteristics. And for the azimuth direction, they are quite different. For example, in the regular radar, if you have an X-band radar with a 3-meter antenna, you put on the airplane and flow it, you can achieve the resolution in range direction like 6 meters, azimuth resolution 30 meters. However, if we move to the space, you put a large antenna, okay, like a 12-meter antenna, a huge one, and then you put on an 8-sound synchronized orbit, you still get the same range resolution, but azimuth direction resolution is very, very poor. It's 2 kilometers. So that's not really suitable for the detailed observation we plan to achieve. So SAR, however, synthetic aperture radar use a different technology. So the engineers build this good instrument, then that using the coherent radar signal processing technology, and the azimuth direction can be achieved in the tens of meters. Okay, so you basically move a small SAR along using the movement of the radar to achieve the very high azimuth resolution. So that's the motivation for put this type of instrument in the orbit. So basically, the synthetic aperture radar is a coherent radar system, and usually we have X-band, C-band, and L-band radar that all have been launched. For example, X-band launched by German DLR, C-band has been launched by Canadian Space Agency, and L-band by Japan JAXA, so on and so forth. So we can achieve very, very high resolution. The SAR instrument is not on always, so it's not always on the orbit. So you have to, we can control what type of mode of data we want to collect. We can get a very high resolution measurement in a very small area, or we can have a ScanSAR wide mode imagery covering 450 kilometer swaths in 100-meter resolution. So you can really pick what type of measurement you want to do. So SAR is really not a new technology. It's been invented in 1950s, and this is very powerful instrument for ocean and sea ice monitoring. So the first SAR was on board the U.S. CSAT mission. This is the first ever U.S. ocean-based satellite mission in 1978. And since then, there have been a lot of development. There have been a lot of land applications to generate DEMs, earthquake, flooding, so forth, so on and so forth. And we have a lot of ocean applications. We have the National Ice Center continuous use for ice monitoring, and we have been using it for wind and waves. So recent development include multiple satellites. We have many satellites flying on orbit now, and with different frequencies, different polarizations, and a lot of research techniques have been mature enough that those SAR-derived products have been used operationally. So this is the diagram showing what's flowing on orbit right now. Primarily, there are ESA, there are Sentinel mission. They have 4 satellites right now, 2 on orbits. And Canadian Space Agency have the RADARSAT 2 mission, and the JAXA has ALOS 2, and German, Italian all have their own. So so people would argue that why SAR hasn't been so popular, because since it was first put on orbit in the 1970s, because the SAR data is quite expensive. Those German, Italian, and the earlier RADARSAT missions, they all commercially based, so you have to purchase images. But these things have changed since ESA launched the Sentinel mission, Sentinel-1 mission. Those data are freely available and flowing to our NOAA through a pipe on a daily basis, so we can get those images directly from ESA in a timely manner. So things have changed, so that's why this talk becomes more relevant. Okay, so we can get free data in a timely manner. So this is a comparison of the difference between the passive remote sensing images and synthetic aperture radar. So apparently SAR has working in the microwave band, and there's no impact by the rain or clouds, and it has very high resolution. It can view the ocean and the land day and night, so it has all-weather daylight capability at a very high resolution. The shortcoming is SAR is not, the instrument is not always on during its flight per cycle. So we have limited coverage. Okay, as I said, the SAR operational agency can point SAR to a certain locations during its flight. So ESA, we know, has a lot of effort going on to target those hurricanes. So once there's hurricanes, they try to point their instrument to look at the hurricanes. So we have got a lot of SAR imageries since the launch of Sentinel-1 series. So at NOAA, we started doing this SAR research and operation since mid-1990s. That's because Canadian Space Agency launched the RADARSAT 1 at the time. Since U.S. has helped them launching, so I think at the time the U.S. government get about 17% of data from Canadian Space Agency for free. So we started, looking at those SAR imageries and try to figure out what can be done with those images. So over the years, we have developed ocean surface wind product with hard target detection, to look at where the ships are, oil spills, swell waves, and so on. There are a lot of applications. I just give you a few examples here. Okay, now let's talk about the SAR applications in hurricanes. SAR again, that's not affected by the clouds, doesn't affect it severely by the rain. So we can observe those two-dimensional sea surface roughness underneath the hurricanes. So this is a diagram. The center part, SAR NRCS. NRCS is a physics quantity that measured by SAR. We call it normalized radar cross section. It basically tells you how rough the sea surface is. And then this signal comes in different channels, because we can the SAR instrument can have like HH horizontal and horizontal receiving transmission, different type of transmission and receiving channels. So for full polarization SAR, we have data from 4 channels, and from these NRCS values and spatial patterns, we can derive the hurricane boundary layer rows, we can derive the hurricane waves, hurricane winds, and by looking at the HAR images, we can get some hurricane eye morphology information. So this is the diagram of a hurricane system. This paper first was published, I think, a couple of years ago on the BAMS. And for those fine scale, mesoscale, fine scale structures like boundary layer rows on the left, a rim band, and the small vortices, and the wind patterns that can only SAR can observe, because for regular thermal and IR and viz images, you can only look at the cloud patterns. On the left-hand side of this cover, you can see the relative coverage between the SAR and background MODIS image. So SAR only covers partial of the hurricane system. That's because the limitation of this particular image acquired, I think, in the image mode. If we have a wide swath mode, it could cover most of the hurricanes. Okay. So the first thing we did is again with Jun Zhang from National Hurricane Research Division down in Miami, we look at all the eye shapes observed in SAR. Again, SAR gives you the two-dimensional view of the ocean rough surface. So within the hurricane eye, there usually the wind is calm, so it doesn't have a very strong signal coming back from those scattering signal coming back from the ocean surface. So it turned to be the energy is pretty low, so it's dark. So that's very, very easy identified from the SAR imagery. And then we can develop a whole bunch of pattern recognition method, and to pick the shapes of those eyes, and then group them together. And this is a little study we did using 73 RADARSAT images given to us from Canadian Space Agency, and then 10 EMISAT images from ESA. From these images, you can identify which wave number those hurricanes belong to. Okay, so that's useful for hurricane category. Okay, so this is the statistics we analyzed from this 80 some images, and you can see the mean area within the hurricane eye, what type of what category those hurricanes belong to, and you can see those are pretty very closely. You don't have to do it manually. Again, this is the algorithm that you can tune to pick out this hurricane eye and eye wall directly from the SAR imagery, because in the eye wall usually the sea surface backscattering energy is quite different from the surrounding oceans. And if you can, this is a very detailed image. If you can see them, very fine, very detailed structure. You can basically, if you blow it up, you can see the waves. Very distinguished eye and eye wall structure. Okay, very fine scale. Then we try to understand what the atmospheric boundary layer roles associated with the wind within the hurricane system. Atmospheric boundary layer roles tells a lot of stories about which way the hurricane is going to behave, and it's either thermal or dynamical instability that cause those roles, and those roles align like linear features, quasi-linear features on the SAR imagery. So we can just pick them fairly easily. For here, you see this is the SAR imagery, and if you see there are two boxes. If you blow this up, you can see the detailed structure within this small box A and B. And if you do a two-dimensional Fourier transform, and you can see those directions and the wavelengths of those linear features. You know, there are a suite of publications by people like Rob Foster from University of Washington, or people in Miami, and also us, to show those boundary layer directions and wavelengths are corresponding to the SAR image wavelengths. So we can just run a FFT on the whole imagery and to pick out this hurricane boundary layer row statistics, the wavelengths, the direction, so on and so forth. And this is the spatial distribution of the rows. We can divide the rows into different wavelengths, and you look at the behavior. This is the paper just published on the JGR this month, so you're welcome to to read it. So then you look at the wavelengths with respect to the location of the storm center. And this is the diagram to show the red line is the wavelengths. The x-axis is the distance respect to the storm center. So we normalized by the radius of maximum wind. And you can see the background, the blue line is the wind. So those atmospheric boundary layer rows are closely related to the local wind information. So that tells us something about the relationship between the wind and also the boundary layer distribution within the hurricane system. So whether this information is useful, how useful this information to the hurricane forecast, I don't know, but at least we can. This is some information we can pull from the SAR imagery directly. Okay, so without any distortion. Just do the FFT across the image, you can get the boundary layer rho distribution. Again, boundary layer rho distribution can be easily acquired, retrieved from the SAR hurricane image. But the most important wind distribution is pretty hard, as you can see as I go along with this talk. Okay, so this is something that we can think of in down the road. And also you can see those micro vertices within the hurricane system. This is like a goldfish with 2 eyes. And those are little things that I think can only be observed by a synthetic Aperture radar. And this is another strange image, and you can see the 2 storms on the left-hand side, 1 storm on the right-hand side. So so SAR observed the surface roughness, regardless of what is ocean or land. But these 2 images, I don't know how to explain them, but you can see those storm patterns continues across the land. So basically, you'll see they have the same backscattering effect, from the ocean and from the land. That's very different from what physics tell us. So I suspect those are the volume we call volumetric scattering in the sky. But that has only been simulated in the theoretical studies. So, and now after we give a brief introduction to see what SAR can measure from the ocean surface within the hurricane system, now let's move a little bit closer to the SAR wind. When the SAR illuminate the ocean surface, you got a lot of signal. You have a forward motion. You have the blue arrow is the signal coming from the SAR, and the red one is a reflected energy, to different places. And as the ocean, if the ocean is like a mirror, you won't get anything back. Okay, as you move, as the ocean becomes rougher and rougher to the panels down here, you can see the signals becomes to what we call the scattering in all directions. And some of the energies went back to the radar antenna that can be received by the radar. So as the ocean surface becomes rougher, the backscattering signal is stronger. Like I said earlier, you have a larger NRCS, normalized radar cross section. That means you get a lot of energy back. Okay, so this is the whole basis on why we can measure ocean wind from the basically scatterometer. So this is a comparison. This is on the left-hand side is the SAR wind imagery, continuously produced at NESDIS star in near real time. On the right-hand side is a corresponding scatterometer wind. So you can see synthetic Aperture radar can measure winds right up to the coast because the footprint of the radar is very, very small. Okay, and for scatterometer, because the footprint is big, you miss a lot of data along the coastlines where you need the data the most. Okay, so those are the SAR wind that has been continuously produced at NOAA NESDIS star and are used by the forecasters up in Alaska on a daily basis. Questions?
So how can it, I still don't understand that we talk about the footprint because one surface is constantly moving and the other one is stationary. So when you butt those right up beside each other and it's SAR's flying over and looking down, how can it, does the accuracy of the wind measurement thing go from less or something? Something's got to change at that moment that's not good for a measurement of it.
Okay, so the question, there's a question from the audience saying that how do you, if the wind is constantly moving, how can you measure the wind in an accurate manner, right?
Well, you look at the ocean surface, which is always moving, but the land is not.
Right. Okay. So for the land, we don't measure anything. Okay. So this comes purely from the ocean. For the land, we mask out because to measure the ocean surface wind, it depends on something we call the Bragg mechanism. You look at the millimeter wavelengths from the roughed by the wind, but on the land, SAR does not have any capability to measure wind over land.
How do you mark it off?
It's just
knowledge of the...
yeah, it's just mask out with a land mask. Yeah, so SAR does not measure wind over land. Only
in this image, it looks like
yeah.
there are
Yeah, we haven't. Yeah, it's I probably picked the wrong one. We forgot to put the land mask on top of it. Usually, we process the whole image and then overlay the land mask. But this particular example doesn't have that land mask overlay. Yeah, I should have done it. Yeah. So this is the comparison, the accuracy between we use the mature scalometer wind to validate the SAR-derived wind product. And on the right-hand side is the difference between the scalometer and the SAR. And you can see as we move, this is the west coast of the United States, up in Washington, here's Oregon. And this is the error becomes larger, not the error, the difference becomes larger as your measurement moves close to the coast. And within like a 20 kilometers or so, we don't even have any comparisons. So that tells you the SAR is very powerful in measuring fine detailed winds right up against the coast. Okay, so
From this point, so it's possible to get the inundation also. That should be possible to get the inundation.
yes, inundation, right?
Then you have to adjust the land mass.
Yeah.
Based on the inundation.
Right.
Well,
that's a good point. Inundation is a completely different matter. We have developed. It's not in this talk, but I just briefly highlight for the inundation part. If you have a water over land, some place we have a different algorithm to pick them out. Okay, to pick them out, and then you can do a comparison between earlier images and later images to know the flooding area, and then you can compare with the coastal models. That's the ongoing work, but that's not a hurricane topic I presented here. Okay, so here is the reason why we can measure the ocean surface wind. Okay, so this is what we call a geophysical model we used. On one axis is the backscattering signal energy we received from the ocean surface, the backscattering, and another is other two axes are the look directions of the wind speed versus the look direction, and also the wind speed. So this is the model we build between the wind speed, wind direction, and backscattering coefficients. So you can see, I won't go to detail, but you can see as the wind go very high, not very, I mean, above 25 meters per second or so, this curve becomes flat. That means the ocean surface, in radar side, the ocean surface roughness becomes saturated. So in other words, you increase the wind speed, those regular SAR observations will not, the energy is saturated. So this is a problem for wind retrievals under hurricane conditions. Okay, so this is a regular model function we use to generate the wind speed from Sentinel-1 and the RADARSAT 2, but it won't be useful for the SAR wind retrieval. So this is just another look at this. You know, when the wind speed goes up above 20 meters per second, those backscattering energy does not change. Okay, this is for the copol channel, what we call copol channel, which means you send the radar signal in for example, horizontal polarization, you receive the signal in horizontal polarization. Okay. Okay, so how do we solve it? How do we solve it? This is this is the traditional CMOD we call for the seabed radar wind retrieval. And if you can see, if their instrument has a 0.5 dB errors, your wind retrieval error is just too big, so it cannot be used. Those are traditional, what CMOD 5 or its similar model functions. So we need to figure out a way to get the wind from the hurricanes. So basically, there are 2 ways to do that. First way we used is something called a cross-pole. The second way we get around it is by looking at the wave information. So let me just go one by one. So this is the National Hurricane Research Division down in Miami developed the so-called inflow angle model. So basically tells you how the wind behaves within a hurricane system. And this model has been supported by flight measurements with the instrument called SFMR, and this seems a very reliable surface wind field. And we look at the VH. This means that we send the radar signal in horizontal direction, but receive it in the vertical direction. Okay, if you're so in this way. Okay, hold on. In this way, it is the signal is not saturated because you send and receive those signals in the orthogonal directions. But it requires you have a very good SAR instrument. Okay. So RADARSAT 2 and also DLR's TerraSAR X, they all have this capability. Even the Sentinel-1 is pretty good. So we can build a so-called cross-pole radar model with the input of the inflow angle model together. We develop a diagram that we can derive the SAR wind and the hurricane conditions. So this is the hurricane just the last week, the Hurricane Lane in Hawaii. As I said earlier, ESA has a very great effort trying to point their instrument over hurricanes. So we have acquired 3 images over the course. And on the left-hand side, this one is acquired on August 18th. On the left-hand side is the regular NOAA process, wind process using the CMOD. For example, you get the Sentinel data from ESA. This all coming freely, and then Chris send those images in the processing line, and then it got processed automatically and come out with this very nice image. So this is operational product, nothing, no human involved. This image. It tells you the fine structure of the hurricanes, but there are some issues with it, and there are basically 3 issues. Okay, it's saturation. If the wind is under 25 meters per second, the retrieval is reliable or copal. This is from the copal, means emitting and receiving in both in HH or both in VV. Okay, saturation. And then if you look closely, there's something called all-glass effect, and that's because we cannot accurately define the center of the hurricane. Okay, so in the middle one is the SAR wind we derived from the cross-pole model using the CP3, so-called CP3 model, plus the inflow angle model. So this gives you very, very good hurricane wind retrieval. However, this is not operational. To go to operational, there are a couple of steps missing. Okay, so the advantage is that it has no hourglass effect. There's no hourglass effect, no artificial artifacts, and the wind, the measurements, the cross-pole measurements is not saturated, and you can also get the detailed wind direction. Again, this is the SAR wind image derived from the cross-pole image, but the cross-pole image is not as, the signal to noise ratio is just not as good as a co-pole because you send and receive the signal in the orthogonal directions. So you can see those the same beams that we need to address. I think ESA is actively working on it to resolve those boundary we call beam seam boundary issues. So we're looking forward, to receive their revised product. So, but there are a couple of things missing between the middle part and the left-hand part. Left-hand part is the operational one. Middle one is the research, still in the research mode, because you need to identify a storm center perfectly. Okay. The second thing missing is the maximum wind. To get this inflow angle model correctly, you need to define the center of the hurricane and the maximum wind. So those are the two things we need to run first before we put this image into operational processing. So this part is still missing. So on the right-hand side, it still gives the distribution of the atmospheric boundary layer rows. But right now, we do not do a pixel-to-pixel analysis about this atmospheric boundary layer rows because we don't know that well how it will help us. So, we hope that the hurricane expert can help us understand this parameter a little bit better. So this is the image we get from Hurricane Lynn. So the following day, we get the same. We get another shot at the Hurricane Lynn. Basically, you can see the artifacts of these operational products and the nice and accurate wind retrieval, both in direction and amplitude.
So the one in the middle, what causes the boundaries?
That's because the question is why in the middle there are so many boundaries. This is a beam seam, the radar scan problem. Okay, because this image is acquired in what we call cross polarization mode. So you send a signal in horizontal, you receive it in vertical to eliminate the saturation problem. So the signal to noise ratio is not great. Okay.
And yeah. The boundary layer roll, that would have to be through a layer, right? So you're on the one on the right, it's different than a two-dimensional. You're trying to look at 3 dimensions.
No, boundary layer. So this basically is the Fourier transform of the whole surface. Tells you which way the linear feature line within the hurricanes.
What is the relation of those with the waves?
Oh, that's a good question. So the question is, what's the relationship between the atmospheric boundary layer and the waves? Because they all present similar linear features. For the maximum swell, what we call swell waves in hurricane system, there are two types of waves. One is the swell, one is the wind wave. Swell wave has a longer wavelength, so usually the longest should be like 350 meters, but those boundary layer rows is well above 1 kilometer, so you can separate them quite easily. So this is another shot acquired August 23rd, and you can see again the left-hand side is the operational product. The middle one is the more accurate hurricane wind. Again, those are different tests. The middle one is the product that we're working on. The left-hand side is already, can be generated as soon as we receive the data in a matter of a few hours. So this is the first way to solve the problem using the cross-pole image to get the maximum, to get the hurricane wind. So there's no saturation. Studies have shown that this wind retrieval can be valid for wind up to 50 meters per second and above. And then this is a published result. We did one validation using again from the National Hurricane Center SFMR data, and you can see those bias and standard deviation are quite good. Okay, it's usually at below 2 meters per second, the bias and the standard deviation. I think this is very close to the instrument limit. Okay. So this slide shows the theory behind all this. We look at the rains, the rain waves, and the composite ocean surface, and to figure out which backscattering mechanism dominates under which conditions. So I won't go to detail. So for this cross-pole hurricane wind studies, we have demonstrated that we can solve those 3 issues. Okay, we can capture the hurricane structure, capture the hurricane wind in terms of both amplitude and direction, and present a very high resolution SAR wind field within the hurricane system. We are talking about in the pixel level. The pixel is on a few tens of meters. So we average a little bit that we can generate 500-meter resolution ocean surface wind within the hurricane system. So that's very new. I think it's a very new product. Will be useful for forecast. And we know for regular radar, you send a signal in the copal mode, you're gonna get saturated signal. And then if you get a cross-pole data, you can solve part of the problem, and then you have to deal with the beam same boundary issues. And this is another example that we try to make a detour to get wind through waves. So studies have shown by the by NRL people who are, in this paper we derived the empirical relationship in the 3 domains of a hurricane system, in the right-hand side, behind side, and left, right. So they all have this empirical relationship derived from the wind measurements. So we try to use this type of approach to estimate hurricane wind. So to do that, first we need to get the accurate wave information. So then we can solve this wave period, significant wave height, and wind. These 3, the triplet relationship, have published many times in the early days, and then polished in this paper. So this is not something new. This has been in the research field for decades.
How does the reflected waves, we're going to interfere with it after it hits a boundary like the land or something?
You mean if you have a reflected waves, you're all screwed up, right? Yeah. I'll show you later how we can do that. Basically, if you do a wave spectral analysis, it separates them into different directions. Okay. So the wind waves is in one particular part of the wave spectrum. The swell waves is in one. Yeah. So you can be you can separate them quite easily, actually. And this is a diagram that we can do. I think on the right-hand side is the research paper by Roland Romizer down in Miami, who shows that the wave spectrum, wave period, and the ocean surface wind can also follow a particular relationship. Of course, it's empirical relationship. Okay, so basically you can develop a processing chain to first get the ocean surface spectrum, wave spectrum. If you look at this, those are the spectrum. You can see those are dominant spectrum, and also there are a lot of so-called noises. That's because the wave comes in all directions and all. So the dominant wave spectrum, you can get it. And then you can just use the empirical relationship between the 3. So if you derive the wave correctly, and then you use the research result to tie that with the waves, with the ocean surface wind and the hurricane conditions for different satellites. So this is a study we compared against the SFMR flights, which shows in the yellow line. And that's the NOAA airplane doing the in-flight measurements. So we can run the wave information retrieval from the images, and then get the wavelengths, and then you can use some sort of dispersion relationship to get the other information, and then just use that triplet relationship between the wave period, significant wave height, and ocean surface wind. So this is a validation for Sentinel data. You can see it's fairly reasonable for these 6 hurricanes, but those 6 hurricanes are kind of, not so strong hurricanes, but so the result looks good. And this is, I think this is another study we did for a validated, I think this is for RADARSAT 2, the previous one for Sentinel 1. So you can see these are the results, okay? So for, more or less, the wind you get has a, 10% error bar. So I think that's very useful for hurricane wind measurements. Okay, so this is just another highlight showing how we divide those images into three sections, and you have the flight going through the hurricanes, and then get the image spectrum and use this hurricane relationship, and this is the x, the omega x is the triplet relationship, and then you can get the hurricane wind speed. So this is general technology. So just to summarize, because of the regular radar signal saturate issue, we have to do a detour to get the hurricane wind. So one thing we did is the cross-pol, using the cross-pol images. The second thing we do is to derive the hurricane wind using the wave information. So those are the 2 alternate approaches that we can put together in reasonable time frame for forecasters. And this is the wave that you just mentioned. If they reflect from the coastal, what you're gonna do? Usually the waves do not reflect from the coastline, because when the water gets shallower, those 300-meter wavelength waves will, will break and die down. But they do reflect and refract along the major ocean currents. So this is the Gulf Stream, for example, the Florida, and you can see the Gulf Stream. It shows in a little bit bright. That's due to the marine atmospheric boundary layer instabilities that cause the warm waters to appear bright on SAR imagery. Okay, so you can just get the waves on both sides of the Gulf Stream, and you do a spectrum analysis, and you know how big the waves are, and then you can just look at the boundary. When the waves across the Gulf Stream boundary, they just follow the linear law. So it's very, very simple. It's just like a geometric optics. So this is whether it's in the optical lab or in the real ocean, they all follow the same law of physics. And this is a potential wave product that being researched and developed both in Europe and here at NOAA. And basically, this is the hurricane system, and the color bar represents the significant wave height. Those white segment are the wave directions, and the length of these segments are the wavelengths of the waves. So those are the product can potentially be done automatically, and yeah. And then we also have some hurricane range studies. There are a lot of physics involved for contributing to the backscattering signal from the rain raft surface. Okay, so we have and on the SAR imagery within the hurricanes, you can see the patterns are different. Sometimes the rain pattern shows as a dark, sometimes shows as a bright, so it's a B and D, and sometimes they just show all dark. Sometimes bright on one side, dark on the other side. So those are the impact of the raindrops on the ocean surface that either surpass the ocean surface roughness or excited the new scattering term. So this is another study we did, just try to understand each mechanism, the rain waves, the Bradley waves, the volumetric scattering in the sky, all contribute to the rain contaminated ocean surface. And again, you can compare this result with the SFMR measurements. And this is the theoretical study we did just to see how much rain, the rain rate versus the normalized radar cross section. So from those type of chart, you can pretty much understand each term's contribution. So there are 5 or 6 effects when the raindrop hit the ocean surface. So I think this is a summary of my talk. It's targeted on the synthetic aperture radar observation of hurricane system. What I want to do is to show the capability of SAR, what SAR can do for forecasters. So basically, the first part, we can observe the hurricane structure in very, very fine details. We can show the hurricane morphology, the eye shapes, the size, and what's in it. And then with a little analysis, we can extract the rain band, the arc cloud. We can look at the boundary layer role and its distribution. And we can tie that to the local hurricane winds. Okay, and ocean surface wind is under hurricane conditions is just one very, very difficult parameter to measure, regardless what type of instrument you use. But SAR do offer promising techniques that we can resolve those high resolution surface wind within the hurricane system. So the validation result shows, against the SFMR measurement, shows the bias and the standard deviation are reasonable within a 2 meters per second error margin. I think if you can get to that magnitude, that's pretty good. And we propose 2 methods to get around the radar saturation issues. One is by looking at the cross-pole signal. The other one is to look at the wave information within the hurricane system. Using both methods, we can derive the hurricane wind on the order of, for cross-pole, I think on the order of 500 meter spatial resolution. For the swell part, it's a little bit worse. I think it's on the order of maybe a few kilometers, because you do need a big box to do the FFT. And most of this presentation is it shows the research capability of what we can do. But as I pointed out, we do have a very reliable, very robust SAR wind processing system at NESDIS STAR to take care of most of the processing, and we know the errors very precisely. We know how good the wind product is. So this will be the next step to take the wind SAR wind processing to the hurricane conditions, that we can produce a good product. One more thing is that to run the process is fairly quickly. So from the SAR data hit to the satellite dish to forecast the desk, the major hurdle is just to get the data from the space agencies, whether it's from Canada or from Europe. So once we get the data, it's all thrown in the pipeline pipeline can get automatically processed very, very quickly. Again, we have 2 books, one edited by Chris Jackson on the right-hand side, and there's another one, fairly new one, just came out a few months ago. It's a hurricane monitoring with Spaceborne SAR. There's 16 or 17 chapters in there, detailing all the capabilities of this instrument, and you can get both on Amazon. Again, those are the papers associated with this talk. I'm going to leave it there. This concludes my talk. Thank you very much.
Do we have any questions in the room?
Some question, but if there is anyone online, maybe we can give.
Yeah. We have a few questions online.
We can ask later.
Okay. Thank you, Dr. Li. We have one question online that goes back to the beginning of your talk when you were indicating the HV/VH. Did that mean the ratio of those?
No.
Can you repeat?
No. Actually, radar signal, just like optical signal, you can send the signal and let the electromagnetic wave oscillate in one direction. Okay. So for regular COPO, the radar send the signal, also it received the scattering signal back. Okay, so when the radar radar sitting in a spacecraft, it sends a beam to the ocean surface. If the surface is rough, it receives its back a scattering signal. Okay, so for the radar, I can manipulate my EM wave in the horizontal oscillation direction. We call it the H-pole. And then we receive, or receiving radar, I can let the receiving radar only receive the signal in the vertical polarization direction. So that's called VH. Okay, I send a EM wave in the H direction and receive the EM backscattering EM wave in the vertical direction. That's called cross pole. Okay. So it's the same thing as optics. I'm not sure if you remember the high school physics class. There's a Malusi law. You have two pieces of glasses. They all have different polarization. If you rotate the two glasses, the optical intensity changes accordingly.
That sounds great.
Yeah.
I'm not seeing any more questions online, but
Yeah.
I have one question. So this, the first generation of SAR was just using one ray, and then they started doing like this double.
Correct.
The TRASAR is the second generation, or they are different?
Okay, so the question is the first generation SAR versus today's SAR. The first generation, for example, CSAT back in the 1970s, it only has a COPO. Okay, it's L-band. You only say there's HH or VV. Because the HV, the signal to noise ratio is just pretty bad because the signal is low. Okay, the same in one direction, you receive in the vertical direction. So the signal is very, very weak. So only the recent SAR has this full polarization setup, and TerraSAR X and Tandem X, both of them have the full pole capability.
And the other one that you mentioned that right now we have free access to the data. Those also have this because it seems like that we can use TRASAR to infer current, surface current, but it is not possible to do it with the other kind of SAR. I don't know why.
Okay.
What
Okay.
has extra?
Okay. All right. The question is why TerraSAR has extra to measure the ocean currents. To measure the ocean currents, it doesn't use the backscattering signal. It uses something called Doppler. Okay. If you can get a good Doppler information, so over the major ocean current, you can get the current direction, the current speed in that direction, in only one direction. Okay. So TerraSAR is a very good instrument. It gives you that, and also I think people have done that to using NVSAT and even Sentinel-1 to measure the Agulhas current of the South Africa. And I think in that regard, if you do the Doppler processing very accurately, you can derive ocean current. Just yeah, all those new generation SAR satellites can do that. Sure.
I think that's all the questions.
All right. Thank you so much.
Thank you.
Thank you so much.